Fructose, after glucose, the next is our fructose. Formula wise, both are molecular formula, both are same. And another name of fructose is called as fruit sugar. You can say ketohexose because it has ketonic groups, or you can say pentahydroxyketone. This is found in cane sugar in large quantities. In honey, it is also found along with the glucose. Polymer of fructose is called as inulin. So this is also one of the important questions. And one of the most important thing is that when fructose occurs in natural forms, so it is actually a laboratory. So unlike glucose, we have glucose is dextrose, but this is your laboratory. So it's also called as levulose. It's also important person. Levulose and glucose is dextrose. How you can prepare? So you take the cane sugar, which is actually dextrorotatory. So upon hydrolysis, in presence of dilute H2SO4, or you keep this invertase enzyme, so this will convert into two molecules of C6H2 and O6, but this will be your D fructose and this will be a D glucose. Already we have seen, but this is dextrose, this will be your D glucose with negative sign. So both are equimolar, but one will be your dextrose, another will be levulose. So this levulose is called as invert sugar. Why invert sugar? Because if you see the specific rotation of this your cane sugar is 66.5, and upon hydrolysis you will see the equimolar, the resultant solution is minus 19.85. So because of its anti-clockwise rotation of this glucose molecule, so this is mixture is laboratory, and this process inversion, the mixture is actually a laboratory despite of dextrorotatory. So this is the basic reasons for preparation of fructose from cane sugar. So we'll get the fructose in large quantities here. And sweetness, you will see that as compared with the sucrose is your 0, but invert sugar is your 100. As compared to sucrose, 100 times of sucrose. Glucose is 70, while galactose is 32, and lactose is 10, and fructose is 170. So you can see fructose is very sweet sugar, so it's called as a fruit sugar. And in this case, when you get this fructose and glucose, this is a crystalline out. So remaining acidic part of the H2SO4 is again neutralized by the milk of lime, that is calcium hydroxide, and you will get this crystals which is filtered. So glucose plus fructose with milk of lime, so you will get here C6H11O CaOH, and this is calcium glucoside or calcium fructoside, fructosate, and this is glucosate. So if you pass this carbon dioxide in this two calcium glucosate and fructosate, so you will get here fructose again and plus calcium carbonate as a insoluble. These two are insoluble in water. So upon passing CO2, you will get the fructose again and calcium carbonate as a crystals. Next, fructose is generally manufactured with the help of inulin. Inulin we have seen it is a polymer fructose. So on hydrolysis in presence of dilute acid, so you will get the fructose, and excess acid again remove as a barium sulfate. Properties: it is crystalline substance or compound, melting point 102 degrees centigrade, soluble in water but not soluble in benzene and ether. So in these two, solvent are soluble but less soluble in water as compared to glucose. Glucose is more soluble, fructose is less soluble. Fructose is sweetest of all sugar, already seen, it is 170 times of sucrose, and it is called anomers of fructose. Fructose is two type of rings. One is 5-member ring, second is 6-member ring. 6-member rings are very small quantities, while the 5-member ring is called as Furanose. It is found in more frequently there. So you can see how it is forming the 5-member ring. So this is the carbon 1, 2, 3, 4, and in 4 this lone pair will attack on this carbon. So we will get this structure, and this carbon is hemiacetal, we have seen in previous sessions. So this is 5-member ring, and it is most stable rings. So we can see here, this is the fructose, this is the open chain structure, and this is how oxygen lone pair of this oxygen attacking on this carbon, and hydrogen shift to this oxygen. So on shifting, this will undergo equilibrium. So we can see, so CH2 is the first carbon, and we will get the structure like this one. So this is the structure is alpha D fructose, and specific rotation of this is minus 21 degree. And the specific rotation of this open chain structure is alpha minus 92. So it is again increasing to alpha D fructose. OH is in the box is your alpha, and when OH is outside, it is called as beta. You can see here. So again, this is forming to this one. So this is toward the equilibrium mixture. This in equilibrium to this and this two alpha and beta D fructose. And here specific rotation is minus 133 degrees. So mutation of D fructose to alpha D fructose to beta D fructose is, this is our beta D fructose is again different, is again decreasing. Even we have Haworth projection formula for the fructose, so which is very less small quantities. So we can see here the oxygen is taking on the first carbon, but these two structures found very less. This is your alpha D fructose or alpha D fructopyranose. Similarly, OH is up, so we'll get beta D fructose or beta D fructopyranose. But these are found in very, we can say, less quantities is there. So despite of stability is very less. Now we will see the furanose structure, which is quite stable. So this OH, so we can write in 5-member ring. So in this oxygen is kept top. So this oxygen is again alpha. So this oxygen is kept top, and this CH2OH is on same side. You can see here starting from 1, 2, 3, and 4. So second, this is your first carbon. We can see here. So first, second, third, fourth. The fourth carbon is your, we can see no, this is the second, 1, 2, 3. So this carbon is your here, and this up position you can see here, and this CH2 is again we have this position. So these are down, so down is there. Similarly here CH2OH is your again down, H is again here you can see down, OH is up, this OH is again down, and then H is up. So these positions are the down areas. This also down, and this is your up. So we can see. So this is your beta D fructose. So this is the pyranose structure of beta D fructofuranose, and in this you can see both methanol are in opposite sides. So both are in opposite sides, because these two are in opposite. One is inside box, one is outside. Here both are outside. So this is basically difference between the alpha D fructofuranose and this beta D fructofuranose. So both are in levorotatory. Similarly, ribose and 2-deoxyribose, they exist in furanose forms. You can see here, these are the alpha D ribose and beta D ribose. So this OH is downside, so this is your alpha D, and you can draw the diagram for alpha D ribofuranose in Haworth projection. Glucose and fructose generally they show similar reactions. So like glucose and fructose, the reactions similar, and there is a positive result for the Benedict. So in Benedict solution, Ferring solution, and Tollens, so they will give the positive test, both glucose as well as fructose, because they will give this positive test. So here you can see the isomeric forms of the fructose. So this is the D fructose, and you can see how this lone pair of oxygen is fifth carbon is going towards the oxygen. It is going up, hydrogen shifting to here. You will get the alpha D fructofuranose. Similarly, this is the alpha D fructopyranose. So this is the OH is again attacking on this carbon. So this is going up, and you will get this structure alpha D fructopyranose. So these are the isomeric forms of fructose, and we have discussed that the furanose is more frequent than that of alpha D fructopyranose. But we will get the both the structures. This is less quantity, this is more quantities. This more frequent. I am repeating it. This is more frequent, this is less, but both are possible. And once again you can see the structures with D glucose and D ribose. You can compare it. This is glucose, and you can see this pyranose structures of both alpha and beta. This is alpha, this is beta, because the alpha OH is down and beta and OH is up position. This is the pyranose structures. And D ribose is your furanose structures. You can see here the OH is again this side. So this OH is your alpha glucose, and we can see same. You can see beta, OH is up and CH2OH is down. So both CH2OH is up position, is beta D, and here CH2OH is single side is called alpha D ribofuran. This ribofuran, this is your fructofuranose. So this is for fructose, this is for ribose, and this is for glucose. I hope you have understood till now. Now we will see the comparison of glucose and fructose. This is the molecular properties. Properties, the glucose both have same formula. Nature-wise, this is polyhydroxyaldehyde, while this is ketone. Melting point for glucose is 419 Kelvin, 375. Optical activity, this is dextro, this is levo. Ethanol, this is almost insoluble. Glucose is almost insoluble, this is soluble. Oxidation, it will react with the bromine water, concentrated acid. So glucose will react with the gluconic acid. Fructose does not react. So this is the only reaction which separates glucose from the fructose. And with conc nitric acid, you will get the mixture of glycolic acid, tartaric acid, and trihydroxyglutaric acid. Here you will get only one, that is cyclic acid. This also differentiates. So this point is very, very important. So only glucose difference between the glucose and fructose. Reaction with sodium bromide or sodium amalgam. So you will get d-sorbitol. Here you will get sorbitol plus mannitol. So only the configuration is changed. Again with calcium hydroxide, you will get the calcium glucosate soluble in water. Here calcium fructosate, which is insoluble in water. Already we have seen this one. Mollis reagent, it will form violet rings. Here it will also violet rings. Toluenes, phenyl hydrogens, both will form reactions. Phenyl will give you red precipitate both. Toluenes will give you cerebroamide both, and phenyl hydrogen will give you oxygen, both will give oxygen. With the resorcinol dilute, that is HCl, this called as Selvinov test. So no coloration. Here it will give red and brown coloration in case of fructose. Pinov test, it will give blue color. It will give you bluish green color on heating. And alpha naphthol plus concentrated HCl, that called furfural test. So glucose will not give, while the fructose will give the purple color on boiling. So we have seen glucose and fructose, glucose properties, test of glucose, usefulness of glucose. Similarly, we have seen the fructose also, its cyclic natures, and finally we have compared between glucose and fructose. Thank you very much.